Let's look at the AWACS, which has been out there for enough time to say a little bit about it. It's a 10-centimeter S-band radar that has a range of about 250 miles. It has a high PRF waveform to reject clutter in the look-down mode, and it has a long range beyond the horizon surveillance mode when there isn't clutter, and also a maritime surveillance mode. So it would be the Radar System Improvement Program, RSIP, would add these advances to the radar system, which is in the AWACS system. Advanced pulse Doppler waveforms, pulse compression would be added, and the detection range would be doubled over the original radar. Now here's a picture of that radome, which actually physically rotates while the radome rotates while it's in operation. And here is a photograph of the actual phased array, which is 26 feet long and 5 feet tall at the center. And it has been designed to have ultra low side lobe array, and it's elliptically shaped. There are 28 slotted waveguides with over 4,000 slots. And the antenna is mechanically scanned, not within the radome, but the radome scans. And it uses 28 reciprocal phase shifters to scan in elevation. And its rotation rate is 10 seconds. It's a beautiful electromechanical marvel to see. It must be 15 years ago I saw it at Westinghouse, now Northrop Grumman. And it's just a beautiful achievement in technology. Specifically when with its very low side lobe antenna was designed in many decades ago. Now let's talk for a little bit about displaced phase center antenna concept. I alluded to the fact that we've got to do something about the spread of the clutter, particularly if you've mounted on the side of an aircraft a phased array radar. We've got this very broad clutter that fills up a big piece of the Doppler spectrum. And this is a cartoon which shows you how that concept can work. And in its simplest way. It shows you, oh yeah, you can do it. You've got here on top of an aircraft an antenna, a phased array antenna, that's whose slotted antenna that's going up and down and up and down. And it's got two sections of it, but neither one is different than the other. Now, while the plane is traveling, if at T1, the aircraft is located in this above section, and the airplane moves in the time T2 minus T1, and if that time T2 is chosen so that if we illuminate a patch of ground at time T1, at time T2, the radar phase center of the beam we make is exactly in the same place as previous. We're not talking about moving the antenna. We're talking about moving the elements that we radiate. So then you've reduced the clutter. You've reduced the motion of the clutter to zero. It's like having a stationary platform in space, but what you've got is a stationary phase center of the illuminated second pulse at the same exact physical place of the first pulse. So if the aircraft motion is exactly compensated by the motion of the phase center of the antenna beam, then there will be no clutter spread due to aircraft motion, and the clutter can be canceled with a two-pulse canceller. And that is the crux of how the displaced phase center concept is implemented. But life is not always easy, and you've got things that you might say, you basically got to get the gain pattern of this antenna, the antenna formed by this side, to be exactly the same gain pattern of this side. If you want to cancel down to 40 dB, you got to have the same gain pattern down to 40 dB. And with reflections off of wings and all sorts of vibratings and all sorts of factors have to be taken into account, which make this an incredible technical problem to solve in the antenna regime. Now, DPCA can also be implemented in mechanically scanned airborne early warning radars. Say we have an individual clutter scatterer alpha off the beam center in beam 1, and then it'll have a different gain in beam 2. The mechanical rotating antenna on a moving platform that generates two overlapping beams can act as a DCPA when the outputs of the two squinted beams are properly combined. And what we do is we take the sum and the difference of the two squinted beams. The sum is used for transmit, and the sum and the difference are used on receive. A phase advance is added to the first pulse, and a phase lag is added to the second pulse of the beams taken. The added or subtracted phase shift depends on the aircraft velocity, the PRF, the scan angle of the radar relative to the aircraft direction. The two signals are subtractive, and that results in the cancellation of the Doppler spread and the clutter. Now, to look at this with a little more detail, you can look at beam 1 as having, I think I've got these mixed up. This is E2 and here in E2, but I've got beam 1 and 2, and the colors are mixed up. But if you've got one of the beams at E2, the other along this axis, and this is phasor representation of the clutter echoes from two successive pulses, you've got 2 eta as the difference in phase. Now there's a correction. If you apply a correction, E2 equal to minus J E2 tangent of that angle and plus J E1 tangent of the phase angle, the half of the phase angle between E1 and E2. Then what we'll do is we'll get two vectors that are on top of each other, and in other words, you can be canceled. And if the sum of the two pulses received is this sum received, delta received, and as I said before, the sum on transmit, the sum and difference on receive, after much manipulation, and you can go read 3 pages in Skolnick to go over it, the corrected received pulses become these, for pulse 1 and pulse 2, and the constant K accounts for differences in the sum and delta patterns, as well as a factor T for the time between pulses divided by the size of the antenna. So you can look at this in detail to understand the math of the when DPCA is used in a rotating airborne radar. Now, the multiple antenna surveillance radar program was, I'd say, the grandfather of, no, it was the grandfather of joint stars. And back in the mid-70s, Lincoln Laboratory was funded by DARPA and the Air Force to test out this DPCA concept. And here you can see the rows of elements, and and they were mounted on a de Havilland twin otter. And when the radar would point down, this is the main beam clutter that you'd see. And you can see here, and this is, of course, a test aircraft, the ranges are going, the range axis is from 28.3 kilometers to 29, almost 30 kilometers. But the velocity is very small, from -3 meters per second to +3 meters per second. And what you want to do is you'd like to see relatively slow-moving targets in this massive main beam clutter by using the DPCA technique. Well, when the DPCA technique was turned off, this is what you saw. And when it was turned on, here's what you could see, sticking up just the target. And a lot of the times, I'm not sure if this test target was what we used, but I know we took it to a nearby. You want this to be fairly large, this main beam clutter. And there's Mount Monadnock is it's a relatively small mountain, but it has a relatively flat plateau. You can drive up it, and it's 1,002 feet above sea level, and it's got many acres of land, and at the top of it is paved. You can take a picnics there, and it's a great place to take this kind of instruments. So we sent one of our staff members up on top and put a corner reflector on his bicycle and a nice speedometer on the bicycle, and drove it back and forth along the tarred road. And I'm not sure if this is an example from that corner reflector, but we were able to see that you could get rid of clutter many, many tens of dBs worth. And just pull out the target nice and easy, and you can see the relative power levels. This is probably 10, 20, 30. This shows 40 dB of clutter in places. It's hard to read from that graph. And here we're up around 20 dB. But it showed the concept work. And then the Air Force put out a contract to Grumman at the time, and for a PAVE mover program where this concept was evolved, and it was put on an F-111, and it worked magnificently, and then it evolved into the system we now know as Joint STARS that worked so magnificently. Here's a photograph of the plane during the first Gulf War. And here is the antenna. It's the frequency changed from L-band in that first Lincoln Lab prototype, pre-prototype. It employs an interferometric SAR for airborne target detection of ground vehicles and imaging of ground and surface targets. And it uses the APY-3 as it's an X-band radar, and it's located in this pod. And the mission of wide area surveillance coverage is over 50,000 square kilometers, and detects, locates, identifies, and classifies these. And these are these numbers came out of both Merrill Skolnick's his handbook, where the system is discussed, the third edition, the third edition of his Introduction to Radar, and also a paper by Burt Fowler that he gave on the Joint STAR. It was published in the IEEE, the Transactions of the Aerospace and Electronic Systems Society of the IEEE. Here's a picture of the antenna. It employs a slotted array, 24 feet by 2 feet, and it has 256 by 28 horizontally polarized elements, and the beam scans plus or minus 60 degrees in azimuth, and it is mechanically rotated in elevation so that it can be shifted to look for one side or the other. And the aperture as a whole can be used for SAR mapping, And when the total aperture is divided into 3 independent apertures in an interferometric mode, it's used for moving target detection. And the moving targets are separated from the clutter by different time of arrivals. The 3 apertures and DCPA techniques are used to cancel the main beam clutter. And this is the famous picture that was released to Newsweek by Secretary of Defense at the time, Cheney, which he called the mother of all retreats. And this is Kuwait City during Operation Desert Storm in February of 1991. And this is Kuwait down here, and it extends lower. And you can see a great deal of traffic up on this road. These are Iraqi convoys moving in that direction. And you can see what General Schwarzkopf called the Hail Mary play. Here we can see those corps moving up in this direction to cut off the Republican Guard. You can see how this type of airborne radar system can revolutionize for the battlefield commander right up to the 3-4 star level just what the enemy is doing. From being back behind his forward line of the battle area, looking forward. And now on to airborne synthetic aperture radar. The SAR basics are going to be covered in Lecture 19, which I hope to get together. And military and civilian remote sensing missions will be discussed in that lecture if I can get to it. I haven't developed that lecture yet. And now to talk a little bit for a moment about ground moving targets. Ground moving target indication use low and medium PRF pulse Doppler radars. The PRF is chosen so that the Doppler region of interest is unambiguous in range and Doppler, and KU and KA band are often used since fixed minimum detectable Doppler velocities allow detection of lower velocities than X band, and the APG-67 and the F-20 fighter has a GMTI mode using the medium PRF, and AWACS has a low PRF mode, ship detection mode. And side-looking airborne radars are a previous technology that standard airborne radars subtract sequential moving target images of the terrain to detect targets. Now, synthetic aperture radars with MTI. Synthetic aperture radar, again, as we're going to talk about it in Lecture 19, if hopefully I get to it. Good cross-range resolution is obtained by processing sequential target echoes as the aircraft moves a distance L, and the cross-range resolution is inversely proportional to the length of the distance moved, not the size of the aircraft, and that gives you the good cross-range resolution. Moving target are distorted and smeared in a SAR image, and they can be detected if the target Doppler is greater than the bandwidth of the clutter echo. And it requires a high PRF to avoid aliasing issues. And Joint Stars uses an interferometer of clutter suppressant processing. Now, in summary, I think that brings us about there. Difficult ground radar clutter environment is the chief radar design driver for airborne radars. Elevated radar platform implies ground clutter for a long range, and both Doppler frequency of the clutter and its spread depend on range platform and scan angle. So just all those variables. It's difficult. We've gone through it. Clutter is the main challenge for airborne radars. The aperture size can often limit you in frequencies, so we have to go X-band at fighter aircraft, and Doppler spread on ground clutter, particularly when you're viewing broadside with these bigger surveillance radars, can degrade performance, and you have to use sophisticated techniques such as DPCA and medium to high PRF modes to handle, and that implies higher power, those medium and high PRF modes. And ESA actively scanned arrays, and significant advances in signal processing techniques such as STAP offer new capabilities for dealing with these challenges. Now, these are the homework problems for this lecture. There's a bunch of them from a Skolnick's book, and then there's this one. I want you to show that the maximum Doppler frequency of ground clutter as seen by an airborne radar is F sub D is less than, where the variables are defined here. And I want you to show mathematically that an airborne radar flying at a constant height, you name it h, above the ground and lines of constant Doppler, you give it the v for the platform velocity. Show that they're a set of hyperbolae. And next is a significant list of references. And I'd like to thank Niall Duffy, Mark Lena, Dr. Alan Hearn, and also from Northrop Grumman, who have helped out a great deal.